Okay, so getting started today, I on all but group 7. So group 7, I'll have this done by the end of today, but I've graded your final project proposals. And what I've also done is extended the availability until this upcoming Sunday. So I want you to look at my feedback, look at the scores you got. If you would like to make changes, then I'm happy to regrade those changes between now and Sunday. So that's your kind of opportunity to take feedback from me to kind of better idea what we're looking for. If you're happy with your grade, and then you can go on and go forward and don't worry about it. But if you'd like to resubmit some modifications or changes, you can go ahead and do that. So the due date is still in the past, but the availability date will be up until next Sunday. And then you can feel free to upload those submissions. So take a look at my feedback. Group 7, you're the only group that has not received a grade and feedback from me. And I just got bogged down with some other things this morning, and I didn't quite allocate enough time to do that. So I will have yours done after class. So if there are any questions about that feedback or anything, then also feel free to either send me an email or leave it in the comments, and I'm happy to make some clarifications. If you want to go through a couple of rounds, then that's fine too. Okay. So moving forward, I hope you kind of noticed now that last lecture we had on the kind of SIR model and epidemiology. This lecture, this BAS diffusion model. And so from here on out, basically every lecture is going to be a sort of case study in how to use system dynamics modeling to do hopefully interesting things in gaining insights about systems. And so these are the types of things that I'm hoping that you'll do for your final project. So in the example of the SIR model on Thursday, they built a basic model of disease spread and used it to experiment with things like understanding quarantine policy. And so one of the things that we found with that is that, for one, before even getting to quarantine, there were these 3 parameters that if you changed any of these 3 parameters, they would affect the population that was protected by herd immunity for this disease spread. And so this contact rate, this infectivity, and what am I thinking of the 3rd parameter right now? Yeah, so, well, we'll see it pop up again here. I don't know why I'm not thinking about it right now. If you can think of what the 3rd parameter is that goes into R naught, then feel free to put it in the chat. It's just not coming to my head right now. But these 3 parameters together, the idea was these go into the model and they have this interesting relationship that if you multiply them together, you get a number. And that number basically tells you how many people are going to be, or what fraction of the population are going to be protected by this so-called herd immunity. And so that is kind of an interesting thing that we found from that. The other thing we found is by adding a small modification to the SIR model, implementing quarantine policy at different levels. So, when you have a certain number of people infected or a certain, larger number of people infected, or maybe you don't ever quarantine, then what we found is that the total number of people who are affected by the disease isn't affected much by quarantines unless you quarantine super early. But what the quarantines do is they flatten this infection curve, which can make the disease easier to handle in the kind of public health infrastructure. So those were things that we kind of learned that we maybe couldn't have guessed ahead of time without the model. And so we are going to do similar scenario analysis in this BAS diffusion model today. And these are the types of games that I hope you'll play with the models that you're building for your final project. All right, so getting into that chapter. So we jumped straight into chapter 6. We skipped over chapters 4 and 5. Chapters 4 and 5 talk about things like delays that we got into last week as well. But in chapter 5, which you didn't read, but there was this nice figure that I'm showing you here, where Morecroft kind of gives an outline of the system dynamics modeling process that I'm hoping you're feeling like you're going through now with your final project. And so the first step here is the problem articulation, so-called boundary selection, where you start deciding what variables are in your model. So when modelers talk about boundaries, what they're actually talking about is what what variables to put in, and that effectively draws a boundary around the kind of endogenous forces that drive the system and the exogenous forces, which are going to be represented as parameters coming in from the outside, where we have no idea how those parameters change. We just take them as being constant throughout the rest of the model. So once you've decided on those things, then you have to decide how these things work together. And so in the case of the SIR model, we sort of decided that, well, there's going to be individuals in these three populations, and based on the number of people in these three populations, then they're going to interact with each other, and disease is going to spread with a certain speed. And so that sort of helps us form a dynamic hypothesis for how these things work. And that dynamic hypothesis, if we recognize certain patterns, then we can start making predictions about our model and how it'll behave over time, even before we actually run the simulation. And sometimes having these predictions ahead of time before we run the simulation helps us check whether we think our simulation is running correctly. So it helps us sort of debug this simulation. And then if our simulation is running correctly, but isn't producing the expected patterns, helps us sort of zoom in to see, well, what's going on in this that's preventing it from doing what I might expect? And that might be very insightful. So this whole chapter was about systems that fall under the category of S-shaped growth. So we've talked a lot about S-shaped growth in the abstract here, and this chapter is meant to add another example of types of systems that produce S-shaped growth. So real examples of S-shaped growth here are, some actual data. So this is actual data about growth of sunflowers. And you can see that over a certain amount of time, if you measure the height of sunflowers in a sunflower field, they grow kind of rapidly, like my dog Dexter is kind of growing like this right now. But then at some point, they start rounding off, and they end up reaching some type of terminal height growth here. So that, even though this doesn't quite look like an S because it doesn't have a strong inflection point, we still bundle this into S-shaped growth because there's kind of a growth period and then a limitation period. Similarly, it doesn't have to just be natural growth. It could also be growth in an industry. So we've got US cable television subscribers over here, and these are from 1950 up to the year 2000. And so as you can see, from the 1950s to the 1980s, then there was kind of a slow growth in cable television here. People maybe used a lot of broadcast television, and so the appeal of cable television wasn't quite there. It was maybe more expensive, just there weren't a lot of adopters. But there were, at some point, then they're picked up and there got to be a lot faster growth. And then at some later point, then it started to round off. And that's this kind of market saturation idea that eventually you run out of people who can buy cable. Like, there's just, not everyone's going to want cable. And of all the people who could possibly want cable, then eventually you run out of them. And so that creates a natural limitation. The limitations that, and I'll get to that question in the chat here, the limitations that go on in the sunflower growth might be due to very different processes. But we still produce the same idea. The idea is there is a limitation that occurs in both, which is why we group both under S-shaped growth, even though the processes are fundamentally different. Now, there's a question in the chat about, TV in particular. Is this S-shaped growth maybe going down because of cable streaming? Nowadays, perhaps that cable is going on because of streaming. But if we look at this period here from, say, 1990 to 1995, then my guess is that cables, that the replacement from cable to streaming isn't actually very strong. So this right here is probably market saturation. If we were to continue this curve, then you'd find that maybe in the year 2010 or so, then this thing would not only be leveling off, it would be falling off here. And as I think, it's interesting, my father lives in Columbus, Ohio, and their cable providers have actually started to partner with streaming providers and are actually encouraging their own customers to just buy internet and then buy packages where they can bundle their internet with a streaming provider for a slight discount. So that's, it really shows how these markets change over time. It's my guess that up to the year 2000, we don't have any of that, those sort of shenanigans going on. But I think definitely if this continued out into modern times, year 2010, 2020, that we'd see these things falling off as, and eventually cable just becoming extinct. All right. So then, the other kind of a nice, these are again real data here, and this might really be the best example we have here of market saturation, is because we don't have a replacement for cardiac pacemakers. Is that this is the the pacemaker was introduced around 1960, and this is the percent of physicians who are prescribing pacemakers to their patients. And these are, let's say, cardiologists or something like that. And so initially there's a slow rise, and then there's a rapid rise in the kind of mid 60s here, as maybe the efficacy of pacemakers became well known, the kind of word of mouth process. But eventually there's only so many doctors out there, and you just kind of run out of growth here. I mean, the fact that they've defined this metric in terms of percentage kind of implies that there's going to be a ceiling on this. You could never go higher than 100%. So whenever you're plotting growth of something that is physically impossible to go higher than a particular level, then you know that that is going to generate S-shaped growth just naturally by the way you define the metric. And that actually strongly relates to the types of diffusion systems that we're introducing in this chapter, because in those systems, there's kind of a fundamental limitation that things can't grow to more numbers of individuals who are in the system, who are potential individuals on which the thing can grow. So that's kind of, kind of what's being hinted at here. All right. So all of these systems have in common this S-shaped growth. The fundamental mechanisms underneath them differ. So the way fish regenerate, the way sunflowers grow, the way my dog Dexter grows, the way cardiac pacemakers are adopted by cardiologists prescribing them, these are all fundamentally different. When the rubber meets the road, these are different mechanisms. But the dynamical systems underneath them all, when you actually get to the causal loop diagram and even maybe the stock and flow diagram level, look very, very similar, and they all have a growth period followed by a limitation period. And so from the CLD, they might all be represented like something like this. So we have this kind of generic CLD here on the left, where you've got some growth engine that once the system gets large enough, then a limiting loop kicks in, and that is going to reduce the growth rate significantly here. We have a more specific case over here in terms of market saturation, where again, there's this growth engine, but instead of having carrying capacity like we might have in fish, we have maximum market size. So these are the total number, carrying capacity is like the total number of fish that can live in a pond. And the maximum market size is the total number of customers who could possibly buy the product. And both of them ultimately are going to limit growth. Things can't grow to the sky. You eventually just run out of ways to power that growth. So reinforcing followed by balancing is kind of what we're looking for here. Now, we've seen for the fish stock example, this stock and flow diagram on question 1 of your homework that's due this upcoming Sunday. And just as a reminder, again, for those who came in late, the final project proposal, all 6 out of 7 have gotten 6 out of 7 teams have gotten their grades and comments back. The 7th, group 7, will get their grade and comments back after class. And then all of you can feel free to submit a resubmission that will be regraded and completely replace your old grade if you would like by this upcoming Sunday. So that's another thing, due Sunday. You don't have to do that, just for those who came in late. But this is what you're going to work with on your homework, where you're going to implement this lookup table yourself and play around with these things. The downside of this stock and flow diagram here is it doesn't make the reinforcing and the balancing loop clear. Like, it doesn't break them apart. Instead, built into this net regeneration curve, there's a part of the curve that under a certain density is rising and over a particular density is falling. And with the way that shakes out is that it effectively implements a reinforcing loop for low densities and a balancing loop for high densities. But it's really kind of, you would like to sort of ideally see those two loops that are, in this diagram here. So ideally, we would like to see something that looks more like this, where instead of having a single fish stock that's over here, where that single fish stock's regeneration rate kind of gets pinched off and gets smaller and smaller and smaller as the fish density gets higher. That's what's kind of going on here. We would like to see maybe something that looks more like this, where you've got a reinforcing loop, where if the more fish you have, the more fish you'll have in the future, but also a balancing loop where you have maybe the potential fish, which are kind of like the number of fish that you might potentially add to the current pond. And as you run out of the potential fish, then you're going to slow down the regeneration rate here. So if we had a way to draw it like that, then it makes it much more clear that this is going to show us S-shaped growth. So ideally, we'd like to figure out, is there a way for us to break up this net regeneration right here so that we can build a stock and flow diagram that's identical to the previous stock and flow diagram in terms of its dynamics, but has a lot more clarity in terms of what it communicates so that we can better understand what's going on. So that's what I'm going to try to set up here. Before I go on to that, the specifics of that, I just want to pause. Are there any questions about anything I've been saying so far about what we mean by S-shaped growth and a growth cycle followed by a limiting cycle, or how the original fish loop worked that you'll be working with in question 1 of your homework? And if not, that's fine. Okay. All right. So I did notice that someone on the perusal actually asked the question of what is the benefit to having a diagram that looks like this one, or having an equivalent diagram that looks like this one. And that's what we're trying to address here, is that this kind of version where the carrying capacity, so in the previous version, the carrying capacity is set over here by the maximum fishery size. It's like an external parameter. But in this one, there is no carrying capacity parameter. It's just the total number of potential fish plus the total number of current fish. That's the total number of fish that could possibly ever be in the pond. And so the carrying capacity has now disappeared as a formal parameter and is now informally kind of a combination of the two initial conditions here of these two stocks. And that in some ways seems like I've made things more complicated, but it is my claim that I've actually made it easier to see what's going on in this new formulation. So what we're going to do here is we're going to kind of think about this fish stock. I'm just going to, for now, call this X. So X is the number of fish currently in the fish stock. And so if K is my carrying capacity, then that carrying capacity, if I want to figure out how many potential fish are kind of, it's kind of like they're fish that are waiting to be convinced to become fish. And so I'm left over with K minus X potential fish over here. So the sum of potential fish plus fish stock is always going to be the carrying capacity K. And the flow in between them is just this dx dt. So it's the rate of change of this fish stock here. That's whatever you name this stock, the flow that goes into it, you can think of as just being the derivative of this stock with respect to time. That's just our kind of convention for these diagrams. And if I think about this formula over here, I'm hoping you guys might recall from somewhere, like in SOS 101, this is the formula for the so-called logistic growth. So if you have any population over here, then the idea is that each individual is going to try to reproduce at some rate R. And so these are the total number of individuals, and this is kind of the attempted reproduction rate. But then that gets kind of squeezed off by this limitation here, where this is how close we are to carrying capacity. So if the number of individuals is very close to carrying capacity, then this thing in the parentheses is going to be close to 0. But if this thing is very close to 0 itself, this thing in parentheses is going to be close to 1. So this formula here for logistic growth acts like an exponential growth for small populations, but then it rounds off for high populations. So this is the classic logistic growth formula here. So hopefully that at least looks somewhat familiar. If I take this formula that we can just look up in a book for logistic growth, I can do a little bit of rearrangement. And what that formula, what I've done here is I've just taken this k out here. If I pull it out of this fraction, then that, so this down here ends up becoming a kind of an equivalent version of what's up top here. So basically you can imagine there's a bunch of different ways that I can factor all of these things through here. But if you rearrange this here, so you like this k would cancel with this k. If I turn this 1 into a k over k, and then I combine these things together, this thing in the bottom here is equivalent to this thing up top. So hopefully some of you recognize this thing up top, again, from like SOS 101, just your standard logistic growth formula. And then down here, this is just an equivalent version of it. The reason I've gone through the effort of separating all these things up is it helps highlight things that are already in my stock and flow diagram. So this x divided by k, that right there is just the formula for fish density, which is down here. So I'm already calculating fish density. Sorry about that, I didn't mean to advance so quickly. And so this dx dt, which is just the formula that goes inside this flow, is just these two things, r and k, which we can think of kind of as parameters of the system. And then this is our state variable for the fish stock divided by k. And this thing over here is actually, we can actually think of this as a version of the potential fish that this is like k minus x divided by k. It's like this formula is combining information from the fish stock and the potential fish together, which is kind of what we want to do here with these links so that we can make it clear that there are two loops here. So if I take all of that stuff, then basically this formula here is what goes inside this net regeneration. So what used to be a lookup table based only on fish stock is now a formula that is based on fish stock and potential fish. So basically those two things coming together to calculate fish density, and fish density goes into this formula, which now can be implemented as a formula instead of a lookup table inside net regeneration. So this whole exercise here allowed us to now get rid of a lookup table, which made it very difficult to analyze, and replace it with a formula where now our formulas make it even easier for us to understand the causal dependencies. Because if I look at this formula, it makes it easier for me to see that if the fish stock goes up, then this term over here is going to increase, which is going to make me think that maybe this flow is going to increase. Whereas if the potential fish go up, then maybe this term is going to increase, which ultimately is going to make the number of potential fish decrease over time. This is made even more clear if I get rid of the fish density entirely, and I just call potential fish y instead of k minus x. And that same formula that I had there on that previous slide, I now can write in terms of y, where I've got two stocks. X are my current number of fish, and y are the number of fish that could potentially become fish if they go through the process of fish regeneration. And that formula that I had back here, which used to be based on the carrying capacity, is now based on these two stocks. And this thing right here makes it much more clear that there is a reinforcing loop and a balancing loop here. So basically that was the whole goal here, was to replace this lookup table, which didn't give me any kind of system dynamics insight by looking at the diagram, with an equivalent formula where that formula has an x into y in positions, which if I look at this here, I can say, well, if X increases, this flow is going to increase. And so if I change this to a pen, then I can tell that if X increases, the net regeneration here, well, that is going to increase. And the net regeneration is exactly the flow, so that's going to increase. And I know that this has always got a plus link in between it, so that gives me a reinforcing loop. But if I go back the other way, if I look what happens here when Y increases, that creates a positive impact on the net regeneration, because again, the net regeneration is this formula right here. So if Y increases, net regeneration increases. And then if net regeneration increases, I already got a plus there, but then there is an implicit backward causal link that is negative going back this way, because as this flow rate increases, this stock decreases. And that is what creates the balancing loop here. So by getting rid of the lookup table and replacing it with this formula, where I've made the potential fish and the actual fish explicit, then now I've created a stock and flow diagram that is easier to analyze or easier to understand what's going on. So it seems a little artificial to implement a stock of so-called potential fish, because these things don't exist in real life. But it's another way to handle carrying capacity. It's an equivalent way to handle carrying capacity. And by breaking these things up, then it can actually make the stock and flow diagram easier to interpret. So that was kind of the goal here of showing that you know, if you can portray S-shaped growth with two loops, you should. And that is partly what is kind of the motivation for what they did in the BAS model, as we're about to see. Okay. So are there questions about this formulation? I know there was a lot of math there, and I didn't mean to get too heavy into the math there. I'm not that interested in you necessarily being able to recapitulate every single step of that. But what I do want you to sort of hopefully get from that is that there are two ways to represent carrying capacity. You either can think of a single fish stock in a parameter K, which represents the maximum amount of that fish stock, or as a separate stock that we can call Y, which is just another name for K minus X. And if these two stocks are related to each other in this way, then there is a natural carrying capacity, because you can't get more fish unless you have potential fish ready to be turned into more fish. So once you deplete all your potential fish, you also stop the growth of these fish. And the claim is that even though potential fish is abstract, that this might actually make the system dynamics more apparent in the stock and flow diagram. So there are questions about that? Is it kind of, you know, and maybe a little murky, but at least almost transparent what's going on here? Okay. All right. So now, just to sort of see who's paying attention here. So if we do make this change, so originally we had a carrying capacity parameter that was going into our old fish model, and I've gotten rid of the carrying capacity. So what in this new model is the equivalent carrying capacity? Anybody have a guess? It's related to these stocks. So imagine if you were simulating this, and I said, simulate this with a carrying capacity of 1,000 fish. And then I said, actually now simulate it with a carrying capacity of 10,000 fish. Where does that 1,000 and 10,000 go? Where do you actually implement the 1,000 and 10,000? And I see a couple of comments here. And I like the comments that I see. So just to make this more clear to everybody else, let's say that I initialized my initial fish stock. So I'm going to say init fish stock was equal to 10. If I wanted a carrying capacity of 500, then what should my initial value for potential fish be? And I'll see if I can wait for a couple of more answers here before I confirm or deny. So again, the goal here is to simulate a system with a carrying capacity of 500. And I have said the initial number of fish in the fishery is 10. So how do I set up my potential fish to ensure that the carrying capacity in my simulated fishery is 500? What do I make the initial value of the potential fish? We've seen at least one more answer. All right, see some other answers. And that's right, so there's a couple people have said 490, and that's what I was looking for here. So that's kind of the beauty of this system, is that at the beginning of the system and at all times throughout the system, throughout the system's behavior over time, K is going to be equal to the potential fish plus the fish stock. So if you initialize the fish stock at 10, then the way you set the carrying capacity of the system is you initialize the potential fish at 490. As the system runs, you're going to convert every one fish you lose in potential fish, you'll gain in fish stock, so that the total number of fish will always be 500. So that's how we're dealing with carrying capacity now, is we're taking the potential fish and we're putting them in separate stock that is kind of like fuel that the system uses, and gradually it uses up all its fuel and it stops growing. That's a very different way to model it. Whereas before, we actually had to have a separate parameter that kind of, what I view as kind of artificially constrained our net regeneration rate in a way that just sort of seemed, it just seemed, I don't know, kind of like it was pulled out of the air. Doing it this way to me makes it more clear that I actually kind of am running out of potential fish. So I don't need to create some weird lookup table which maps the current number of fish to the regeneration rate, that it kind of happens naturally through the combination of these two things together in potential and fish. And so that's all we're saying here, that the maximum fishery size is just the sum of those two things together. And so that's where we get that carrying capacity. So if I were to build this thing in VinSim, then I could create like a remaining fish capacity stock and a fish stock, and a birth rate in between them. I can, then the flow that goes into this birth rate is just going to be some parameter R, which will be kind of the number. So I probably should, if I was, being complete here, there should be some parameter R going into this birth rate here. And then that will end up multiplying by the fish stock. And it will then also multiply by the remaining fish capacity, Y. And that whole thing will be divided by this sum, which is actually going to be constant. And inside VinSim, I could create a shadow variable, which is just the remaining fish capacity, which is the same thing as Y here. And I could then create a shadow variable called fish stock X, and then a carrying capacity, which just adds the two of them together. And if I were to plot this thing, it would be constant over the entire behavior of the simulation. It would always equal whatever it started with. So that's how I would implement that. And I would interpret this as being this R times X, which is happening inside this birth rate here. That here is like the potential births per year. And I can then view this thing as the fraction of the potential births that lead to actual births. So this remaining fish capacity is effectively keeping track of the fraction of, that if you think about how many offspring actually survive maybe to reproduction. So let's say every fish manages to reproduce, but there's not enough food for those offspring to survive. So only this fraction of them actually survive to reproduction. So when Y is very large, everybody survives. As Y gets small, then nobody survives. So this remaining fish capacity is just proportional to the probability of offspring survival. So that's another way to view this model, is it's a stock that's keeping track of like how the probability of offspring survival changes over time. And my hope is that when you look at a formula like this, after the SIR model from last week, then this should look a little bit familiar, where effectively we have the, this is a little bit like having susceptibles and infected or infectious populations. And this is like the change in the infectious population. And it is going to be the product of the number of infected individuals times the number of those left to be infected. So it's almost like this population growth has exactly the same dynamics as contagion. And that is sort of the major motivation for this chapter, is that we already know how disease spreads through populations. Can we use the ideas about disease spreading through populations to think about the growth of other things that live on top of populations? So when we think about this fish population, we can then try to figure out how does this relate to the SIR model. And one way to view that relationship is to think that this kind of potential population are kind of like susceptibles, and the infected population is kind of like our, fish stock. And we just sort of forget about this recovered. So you can almost think about this as being infected or recovered or something like that, or just generally affected by disease. It's like you've got not affected by disease and affected by disease. We kind of, grouped I and R together into one stock here. And that's kind of where we're going through here. So that is the basic motivation behind the BAS model, is that the BAS model is modeling innovations like cell phones, cars, as they spread through a population. BAS, it's not about fish. When we think about fish, we actually think about fish reproducing. You had one fish, you got two. You had two, you get four. In this case, we're not actually thinking of things reproducing. We're thinking about individuals already in a population kind of changing their state from kind of one team to another. And so we have potential adopters switching to becoming adopters. And this idea that we have to evolve on an existing population creates a natural limitation. So this potential adopters is the way we're modeling the fact that there can only be so many adopters of a technology. And it is greatly inspired by epidemic dynamics, where in that case, diseases can only ever infect 100% of the population. Diseases can't go over 100%. So they are going to be naturally limited. And the question for public health people is whether you just let them run out until everybody's got it, or do you try to constrain the growth of these things? The question for marketers is like the opposite of that. The question for marketers is almost, how do we ensure that definitely everybody has it, and how do we prevent only a small group from having it? All right, so are there questions about this relationship here, about how this fish population kind of relates to the S and I of the SIR model, and how the SIR model kind of relates to this idea of potential adopters and adopters in a marketplace? Does this analogy, these two analogies, make sense? Or if not, then are there specific questions you have about where the analogy falls apart? Okay. All right, good. All right, so in the BAS model, what determines maximum market size? This is, in this diagram earlier, this, Morecroft brought up this maximum market size, but if you look, there's no maximum market size parameter inside this kind of simplification of the BAS model. So what is the maximum market size in the BAS model? Does anybody have a guess? How do you put the maximum market size inside VinSim when you're drawing up the BAS model. And this goes back to thinking about where is the carrying capacity in the fish model. So I'm just going to pause here to make sure that we're all on board here. So where do we program in the maximum market size? I see a couple of responses. The responses so far talk about potential adopters. I think that's a big part of it. So, but can we be more specific? And then I see potential adopters plus adopters. So that's kind of what I'm looking for here, is that the initial condition of the potential adopters plus the adopters ends up being the maximum market size. So if we think about this as, well, I'll use the same, if we think about this as, let me erase that. If I think about this as Y0, the initial number of potential adopters, and X0, the initial number of adopters, then the maximum market size is just going to be Y0 plus X0. So if you want to simulate 1 million people in a market, then you better make sure that Y0 plus X0 adds up to 1 million. Your X0 are the initial number of people who start with the product, and the Y0 are the initial number of people who don't have the product. And so the total possible market size is the combination of those two. That's how you set up the equivalent of carrying capacity in the BAS model. There is no separate carrying capacity parameter. It's the combination of those two initial conditions. Are there questions about that? Does that seem pretty clear? And it's just the same where in the SIR model, if you want to simulate a population of 1 million people who could potentially get infected with the disease, you got to make sure your initial S, your initial I, and your initial R all add up to your total population size. And so that's all we're seeing as we gradually get into the formulas here for the basic BAS model. Then this gray box here is just meant to highlight this, that this is the adoption process that was abstractly drawn on the previous slide. And we see that the total population, which is this thing here, remember in Stella, the total population is, they've got a funny little variable called a plus in Stella that allows you to choose other variables and have them added together. And it creates kind of a false variable that's just the addition of other variables together. And that total population is just the sum of these things. So that's effectively a constant. It acts like a parameter. That sort of acts like the carrying capacity, K. And then we've got a function of adoption rate from word of mouth here, which is this is the flow that is going to take away from potential adopters and turn them into adopters. And that adoption rate is just exactly the adoption from word of mouth, which is going to be this variable down here. And this variable down here pulls in from these three things that we're going to talk about in more detail here. And so it pulls in from the total population, from the adoption fraction, which we're going to see is how frequently do people who bump into other people who already have adopted to the technology actually adopt the technology they've experienced. And then we've got the contact rate, which is how frequently do adopters bump into potential adopters. There's a question in the chat, how would you measure adoption from word of mouth through surveys? So these three parameters, these two parameters are kind of the important ones here. Those would be ones that marketing surveys could, or marketing analysis could measure. So you could go out and do a study. It might be difficult to get exactly precise numbers here, so you probably have to do some approximations. But in principle, everybody with modern technologies, it might be very easy to do. You might be able to actually install an app So you could say, I'm going to get some of my adopters to agree to install this app on their cell phone. And this app will give me an idea of how often they bump into other individuals. And so that might help you understand the contact rate of how frequently these people see. Or you could maybe do some other analysis where, we mentioned kind of a well-mixed approximation in the SIR model. You could sort of say, well, what we're going to do is put cameras on major highways and urban streets, and we're going to count up how many of our vehicle that we care about versus the other vehicles are out there. And we are going to assume that that fraction that we see is going to somehow relate to the contact rate, so that how often do people who have adopted our technology end up getting exposed to people who haven't adopted our technology. Now, for adoption fraction, that we might have to survey people, or we might have to sort of see, like, based on true, like, if people who go into a car dealership, as an example, we might know that they've definitely been exposed to the technology when they enter the car dealership. How often do they actually end up buying a car versus buying some other car, or leaving? So these are things that are maybe difficult to measure precisely, but there are marketers out there who are doing exactly that, who have built their entire careers on estimating these types of parameters. And you go to those domain experts and ask them, what's the range of these parameters to put into these models? And then you could put those things into them. Okay, now notice that this is a slider. That's what this icon means in Stella, that this is a slider. And by the way, there is a note in the chat that we have a student in the current class who is a member of Venture Devils and has put out a survey as part of his Venture Devils experience. So this is a program that it encourages entrepreneurship and usually involving sustainability and such things like that. And so if you're interested in helping out with that, the survey is in the chat, and encourage you to take a look at that. Not related to this class, but I did give approval to put that in there. So take a look at that in the chat. So this slider here allows you to play around with adoption fraction very quickly, the way we talked about sliders, a week or two ago. So that's what, whenever you see this icon in the book, that indicates that Stella is allowing you to use a slider to play around with that while things are similar. All right, so let's drill down into that a little bit farther. So again, we can have a mental model of the BAS diffusion model as a contagion model, where the potential adopters are susceptibles and the adopters are infectious. And the total contacts per day from the SIR model is like our contact rate. The infectivity in the SIR model is like the adoption fraction. And then again, the total population is the same. It's like our total population. And so this adoption from word of mouth is identical to the formula that we used in the SIR model, which represented how frequently you got a flow of individuals from the susceptible population to the infectious population. Now, are there questions about that? Is the relationship between this BAS model and the SI portion of the SIR model pretty clear? Okay. Now, given that even though this process is very different than the process of spreading disease, we claim that the dynamics are similar. And so not surprisingly, when you simulate this thing, you end up getting things which look like the SIR model. So this line here marked 2, which corresponds to our potential adopters. This is kind of like susceptibles. You start out with a high number of susceptibles and they decline over time. This line 1 here, these are our adopters, which are kind of like our infectious population. And they start low and then they grow up high. And so this is exactly like the S-shaped decline and S-shaped growth that we saw in the SIR model. And even further, if we look at the adoption rate, the flow in between these two, it has a peak that looks just like the infection peak that we got in the I dynamics of the SIR model. So that, those dynamics were kind of expected. Now, what we see in here is that there is a long period of very slow growth. At this scale, it looks like there's no growth, but in reality, it's an engine that is just kind of starting up, and there's very few individuals, but they are growing. They eventually reach a point where they kind of lift off here, and that growth becomes very conspicuous, and then it rapidly rises, and eventually you reach market saturation, and then you're kind of done here. So the question here is, we would ideally we know that this rise is eventually going to happen. So in our case, for market adoption, we would like to speed up when that comes. And so the question is, how do we increase the speed of adoption? And we effectively need a way to make people sicker than they currently are, or make more people sick initially. And the only way we can do that as marketers is by introducing marketing or advertising. And so what they've done is they've taken the old SIR model, and they've added a portion, or SI portion of the SIR model, and they've added something that we probably wouldn't ever add in an SIR model. They've added this weird advertising loop, which effectively makes it so that the more adopters you have, then there is an advertising process which turns them into adopters, even though they haven't interacted with adopters. So that's the key difference between word of mouth and advertising, is that advertising, you're not interacting with someone who's already adopted it. You're spontaneously choosing to adopt the product, possibly due to interaction with the company that sells the product, as opposed to someone who's bought the product. And so this loop here can only last so long because there's only so many potential adopters. It has potentially limited effectiveness, but the whole idea here is that you're trying to get word of mouth going, because word of mouth is going to be a much cheaper and much more effective way to spread the thing through the population. You can't advertise your way to market saturation. Market saturation really counts on word of mouth. If you advertise your way to market saturation, you're going to spend more money on advertising than you're going to make on the product. So this is an initial investment that ends up tapering off over time so that word of mouth can take over the rest of it. And so if we put a little bit of advertising into our model, then what that has the effect of doing is it ends up making these same dynamics of S-shaped decline and S-shaped growth happen after a much shorter time. So we get that infection peak that looks identical to the old infection peak, but he actually gets the peak at a much shorter time. So the company goes from not being profitable to being profitable much more quickly. And that's all due to advertising. So that's really the point of advertising, is not to drive up sales. The point of advertising is to drive up word of mouth. And word of mouth ultimately is what drives up sales. All right, so are there questions about this basic BAS model? And as you think about if there are questions here, let's do I'll put a attendance question in the chat. And that question is, what determines the market saturation size in the BAS model? Is it a parameter or a set of parameters? If so, which ones? All right. Okay, so I'll let you think about that. So moving on here, so what I'm hoping you're seeing here is this general pattern where the BAS model took contagion dynamics that were already kind of well understood in the system dynamics literature, and it bolted on a tiny little piece that allowed them to do advertising. This is a great way for you to think about your final projects. Take a model that you're already kind of familiar with by flipping through the textbook, for example, and make it your own. And so examples of that is we can take the BAS model here. So we've got potential adopters, and our advertising loop. And let's say that we wanted to model a specific product that what was special about this product is that we were interested in repeat purchases. So not just one purchase, but do they keep coming back? And so baking soda is kind of the type of product that we're thinking about here. Baking soda is a beautiful product because you buy it and you initially just dump it. Like people that they buy a bunch of baking soda, and rather than like making use of it, so using baking soda for baking, like depending on how much baking you use, it might take you a really long time to go through a box of baking soda. But they figured out that they could get people to dump all the baking soda down their sink, potentially for cleaning purposes, but that was a great way for them to get more people buying baking soda. And then the people who are already buying baking soda to come back and buy more baking soda. So the repeat purchases became really important. And so you might want to model, well, how do I model sales from repeat purchases? Well, I can take the basic BAS model here and I can add on this thing up to in the top here. So the idea here is I could come up with an average consumption per adopter, and I could then use that to determine a repeat purchase rate. So how often does someone who's already adopted baking soda go out and buy more baking soda? And that will add on to my sales rate. My sales rate will also include the initial purchase rate from those who have just decided for the first time to buy baking soda. So all of these things together end up giving me a sales rate here, which reflects not just the conversion from people who were not using baking soda, also to those who are repeatedly purchasing the baking soda. So that's a way that I can add on to that to make this a much more useful model for more specific cases, kind of moving closer to the realism side of that spectrum, where you've got the analog real side on one side and metaphorical on the other. Similarly, what if I am not interested in baking soda? What if I'm interested in refrigerators? These are so-called durable goods. You buy a durable good once, and then hopefully you've got it for like 10 years. And then after 10 years, you get rid of that product and buy a whole new product. There's no reason you'll buy the exact same product again. So in that case, I can start with my BAS model down here at the bottom, but then I can add on this new set of flows over here at the top. And this flows represents this idea that those who have adopted over a very slow amount of time will eventually go back to becoming potential adopters again, and they might buy a different product. So I put my average product life up here, and that helps model this process of converting back into my potential adopters. So if I zoom in here, this discard rate here might just be the number of adopters divided by the average product life. And I'm hoping that looks familiar to you, because that's basically the same thing that we did in our bacterial process here, where we had like the number of bacteria divided by the lifetime of the bacteria. And we just turned that here into a rate of decline of adopters here, so that overall, we can end up figuring out how many new potential adopters we're going to generate each year, which is what we're seeing there. And so that is a way for us to figure out, basically, let's say when I'm doing design, in order for me to maintain good sales, do I want this product life to be short, where people will be buying this very frequently, but might buy someone else's, or do I want it to be long, where I'm guaranteed they're not going to be buying someone else's, but they're also not going to be buying mine for a huge amount of time? So that might be a question that I might want to investigate here. Now, I'm hoping that when you look at this might look familiar towards the end of that SIR lecture, because this kind of reminds me of a so-called SIS model, where you have those who are susceptible become infected, but then they never become immune. They just become susceptible again, like the common cold. And we know from our SIS model that if we were to look up in epidemiology what happens with SIS models, and you always get a population of susceptibles and a population of those that are currently infected. So you don't get the nice herd immunity where eventually you get to a point where you've got a protected population. You pretty much have a case where there's always some fraction of people always sick. And so that's kind of, this is like a cold here. There's always someone who has the cold, and there's always someone who doesn't have the cold. Likewise, in the durable goods market, there's always someone shopping for a refrigerator, and there's always someone with a refrigerator. And so we're kind of, they have the same dynamics, even though it's a very different process. So that's just a couple of examples of how you can bolt on little add-ons uh, to existing models that we've seen in class to make them a little more complicated, a little bit more related to a specific problem that you're interested in, and get very different dynamics out. So are there questions about that? Is that pretty clear, this idea of modifying existing models? You don't have to start from scratch. The BAS model itself started with a Contagion model and added advertising to it. And there was, I think, so there's a question. So that first attendance question, and I can just sort of tell you here, what I was looking for that first attendance question was just the initial number of potential adopters plus the initial number of adopters. That sets the carrying capacity. I don't grade these things for correctness. I just grade them for completion and coherence. But that was that previous attendance question was just, I'm looking for the sum of the two initial conditions of those two stocks that divide up the population. All right, so so the next thing here is this last, so where we're going to close out here is this scenario that they ran at the end of the book, which I think was a great example of something that, just like in the SIR model, we ran scenarios at the end of the lecture that showed how to use the model. I want you to come up with scenarios that you can run in your own models for your final project that end up telling you something interesting about parameter settings or the fundamental structure of the system or something along those lines. So what they were studying in the textbook is this EasyJet example. So this is a budget airline that is introduced in the UK. It is, low-cost airfare in Europe. And so in '97, this was kind of a new thing. And so there is a major investor who decides that he's just going to buy a whole bunch of Boeing 737s and start to sell these low-cost airfare and hopefully underbid all of the big carriers out there and get so much business that he will end up getting a significant portion of market share, not all of the market share, but a significant portion that it will pay off the investment so that this will become profitable before the other carriers have a chance to catch up. And at that point, when they catch up, then it'll come to kind of a new equilibrium, but at least at that point, he'll be profitable and the other carriers will have lost some customers, but it'll have changed the entire airline business to providing, cheaper airfare. So the question to be modeled here is this even feasible? So in order for this investor to become profitable, he needs to make sure that he can fill 12 of these planes. So in other words, to get 1 million passengers in a year, let's say. So if we go back to thinking about this iteration here, then this is, that we've got this problem articulation and we need to formulate a dynamic hypothesis that captures the dynamics of this problem that we're trying to capture and trying to analyze here. So how do we model the growth of potential passengers? So we're going to kind of build this thing from scratch as opposed to using a standard BAS model. And that's going to allow us to kind of customize this in a way that's more specific to the airline industry. So we've got potential passengers for EasyJet. These are EasyJet's potential passengers. So I'll just put an EJ there. And then we need to, this is a stock. And so we need to model the flow, how they're going to change over time. And initially, we know that the only way we're going to get them changing over time is by advertising. We need to tell them that EasyJet exists. So we're going to add marketing connections into here. So we got marketing effectiveness and how much we're going to spend. We know the more money we spend on marketing, the more potential passengers we'll be able to get as they become more familiar with EasyJet. But we know that there's going to be limited effectiveness per dollar that we spend. So these two things combine to actually get potential passengers interested in EasyJet. So that's what we're showing up here, that this flow is just the product of these two things here. Now, is it possible for us to achieve 1 million passengers by marketing alone? Well, if we actually look at the raw parameters here, we know that let's say we start spending 2,500 million pounds per year, or sorry, 2.5 million pounds per year. And we end up saying our effectiveness is we get 50 passengers wooed per 1,000 pounds spent. Then these things together, if we end up doing a little bit of math, then what we see here is that together at this level, we're only going to get 125,000 new passengers per year. And so if we think about these parameters here, this amount of spending, then if we don't increase our spending, then it's going to take us many years until we actually reach the 1 million passengers we need. Or if we need those 1 million passengers in 1 year, it's going to require us to spend a whole lot more. So basically, it's going to be way too costly or way too slow for us to depend just on marketing. But of course, we know that in real markets, it's not only the advertising that causes growth, it's word of mouth. So we're going to add that word of mouth engine in here. And so we've now got marketing effectiveness, marketing, and this word of mouth. Now, because this is an airline industry where there's existing competitors, then we need to think about how to model the effect of those existing competitors on our word of mouth. And so they've sort of said, well, we're going to create a conversion ratio, which is going to sort of convert the relative fare. So that's going to be, how does our fare compare to their fare? And based on how much we undercut our competitors' fare, that is going to affect how our word of mouth is going to work. So if our customers bump into their neighbors and say, I got a ticket to fly to France for 1/10 the price of British Air, then that's very likely to convince their neighbors that they should check out EasyJet too. But if they say, well, it was 90%, so I only got a 10% discount, then the other ones say, well, you know what, I really like British Air, so I'm going to kind of stick with British Air. That's not really that much of a discount. So we know that the amount of discount between EasyJet and the rest of the carriers is going to affect their the amount of how their word of mouth is going to use here. So that is what's put together in these formulas here. And so this increase in potential passengers, that is our flow that's up here. And it just brings together all of these things together. The potential passengers times the conversion ratio that we're going to show here in a second, and then plus the effects of marketing. Now, this conversion ratio, we don't have a good formula for that. And so we're going to use a lookup table. And that lookup table is just going to plot our relative fare on this axis and our conversion ratio on this axis. And so this is basically going to say that if we were giving away our flights for free, then basically everybody who flew with us is going to convince 3 of their neighbors to also potentially fly with us. That's what this lookup table means here, is if the relative fare is 0, then we get 3 new customers per every 1 customer. Now, if instead the relative fare is up here 1.2, that would mean that that we are actually more expensive than our competitors. And at that point, we're not, word of mouth basically turns off. If we're more expensive than our competitors, nobody's going to come up and consider EasyJet. And there is some fall off that they have modeled with these set of points here. And like you can see, once we are the same price as our competitors, we get no word of mouth conversion. But as long as we are cheaper than our competitors, and that's what this is representing here, so this is the fraction of our competitors' price here. As long as we are cheaper than our competitors, then every 1 customer of ours is going to convince so many of their friends and neighbors who don't currently consider EasyJet to start considering EasyJet. That's what's being modeled here. Are there questions about this lookup table? Does this make sense, this lookup table? Because I know there's lookup tables on your homework. I want to make sure it's clear the ways you can use lookup tables to represent relationships without having to come up with formulas for them. And again, you can think of relative fare as the EasyJet fare divided by the competitor's fare. Okay. Now, that would work if our competitors had 1 fare that they didn't ever respond. But the thing is that our rivals, the competitors here, they're going to notice that EasyJet is introduced and they're going to respond. And so we have to think about how will our rivals respond to the introduction of EasyJet. we have to model the rivals restructuring themselves to make their fares cheaper in order to make the model complex enough to really capture the important points of reality. So we know that the rivals fare changes over time. So that implies that our rivals fare is going to be a stock. So we're going to need to make the rivals fare not just a parameter, but actually a stock. And that means that we are going to need a flow associated with that stock that represents how that stock changes over time. And we might need to determine things that put in new parameters, which will affect what determines that timing. And so that's what they've done here is they've created a stock rivals fare and a flow change in rivals fare. And they've said, well, practically what makes it difficult for the big competitors to change their fares? And that's, well, the structure of their airline, what they pay their flight attendants, what they pay their pilots, how many flights they run, all these things. It's not easy to change their fare because it's going to require making their operation much more efficient. So that's going to take time, this time to change costs here. And so this restructuring loop is going to basically take their current fare, compare it to the startup fare, and based on the difference between those two, we'll try to bring the rival fare close to the startup fare. But that process is going to be slowed down by however much time it takes for them to restructure. And the way that works, and then that will end up connecting to that relative fare. And so the formula that they'll use in this change in rivals fare is basically just a smoothing delay. And so they've set up this process here where we've got the fare set by the startup minus the rivals fare divided by the time to change costs. That's the toilet bowl example right there, where it's kind of like the target, that's the target they want to reach. This is the current level in the toilet tank, their current fare, and this is how slow it takes the water to rush into the toilet, how quickly they can actually restructure themselves. And so when you combine all of those things together, it's basically just a smoothing delay. And so rather than writing this formula here, you could actually use some of those smoothing parameters that we've learned about in VinSim and in InsightMaker. And so you have an initial rivals fare and a smoothing delay, which is just changing how quickly the rivals fare changes into the fare set by the startup. And so that's all I'm kind of hinting here, is that you could use these smoothing delays as well. So that's this formula here. You can just implement the rivals fare with a smoothing delay, where this is what you're trying to hit. And this is the inertia in the system. And this is the initial fare that you have that will gradually change over time into the fare set by the EasyJet. And so that's all that's being set up here. So, so this, I kind of want to, skip ahead here, but the other things that that they go into here is other complicating factors that you could imagine adding on here. As example, they talk a lot about service reputation, and so EasyJet will, attract passengers away from the carriers, but they're going to eventually lose passengers. And if their service reputation changes over time, which is why they've implemented it as a stock here, then that can actually increase how much they're going to lose passengers here. So it might be important for them to keep their service reputation up, and it might be important for them to model how their service reputation will change over time as they get more customers and maybe becomes harder to provide high quality service. So we can put all of these feedback loops together. We have our basic EasyJet model here. We can add in the startup, we can add in the competitors, the rivals, the existing big carriers, and we can add in the churn from the reputational part of it, the fact that not everybody's going to be happy with EasyJet, and they're going to flow out of EasyJet anyway, back into the major carriers. And so this effectively looks a lot like a modified Bass diffusion model in the end, where we have a growth engine, we've got a limiting engine, and then we've got a bunch of things bolted onto it, which change the dynamics to make them more realistic. And so, so that's, you know, we went from our dynamic hypothesis, we went into a formulation, and the next step they go on into the book is testing and policy evaluation and formulation. And these they do with sliders, and those were these plots that they went into in the book here. We're almost at time here, and so I'm not going to go into great detail, but I hope you pick this up in the back of the chapter here, is they basically talked about if the carriers are slow to retaliate, then you can, then you're going to become profitable as EasyJet eventually. And if you spend a little bit more money, you'll just become profitable more sooner. But if our rivals respond much more quickly, then even if you spend a lot of money in marketing, then you'll end up you'll end up being profitable. But if you end up not spending that much money on marketing, then the big carriers who respond are actually going to respond so quickly that you'll never actually reach profitability. So this is really a terrible outcome, which implies that it might be really important to make sure you're spending enough on advertising so you can get out of there and get your EasyJet out before the competitors have a chance to respond. All right, so before I take any questions, I'll put the last attendance question out. Then I'll remind you of some of the announcements, and I'm happy to take some questions if there are any. So the question I have here is what is the definition of a durable good? Going back to thinking about one of those modifications to the BAS model. And that's all the new content that I have for you today. So if that's all you need, you can feel free to take off. Otherwise, if you have any questions, I am happy to chat about those for a few minutes now. And I will go back to the reminders here. Again, muddiest point due Sunday, assignment E2 due Sunday. And then I've also extended it so that you can feel free to upload a new version of your proposal if you'd like, that I'll regrade and replace the old grade with a new grade if you'd like to respond to those comments. And this is just highlighting the readings coming up here. And each one of these is going to kind of be a new case study of different ways to use system dynamics modeling for different types of systems.
I just want to say thanks for shouting it out earlier. Appreciate that.
Oh, no problem. Glad to help.
All right, see you.
All right, looks like everybody's heading out. So I will go ahead and end the meeting. See you all Thursday.